Well, tonight we're going to hit a lot of graphs, and by the time the video's over, I think you're going to have graphs coming out your ears. We're gonna throw a million at you tonight. But our big goal tonight, is to gain a better understanding here of the relationship between a graph of a function and the graph of its derivative. And we're going to be able to go both ways. They're going to give us f and ask us to describe f prime, or vice versa. They could give us f prime or even f double prime and ask us to go backwards and explain f. I absolutely love this picture. I think anytime we get a little overwhelmed or confused in the next couple of days, we want to come back to this picture, and just the great job that this picture does of showing the relationship between f here and his derivative down here. And the bottom line, if we're going to walk away with just one key idea today, I want you to understand this. Do you see the horizontal tangent lines that exist on f? And do you notice what they correspond to on f prime? That's the $1 million idea here. So we want to get this concept down, that the horizontal tangents on f of x, they correspond to who? How are we going to describe this? They correspond to the roots or the zeros of f prime. That's the $1 million question. The other key ideas that you'll recognize here is, anytime f's decreasing, you're going to see f prime living below the x-axis, okay? And then anytime you see f increasing, like this, you're going to see f prime living above the x-axis and vice versa. So that's another big idea. All right, here's a good basic activity to get us warmed up here. They have given us the graph of f, and we're going to complete the chart. And what we're going to do is we're going to just estimate the derivative or the slope of the tangent lines at the given values of x. So what I'm going to do is I'm going to start way back here at x equals -5. And again, I'm just visualizing all the tangent line, and we could, split hairs on this one, but I'm going to just estimate that the slope's about 2. I'm going to estimate here the slope's about 1.5 or 5 or 3/2. Then we'll say a slope of 1, slope of 0 roughly. How about -1 and -1 right there? They're about the same. When x equals 1, we'll say there's about a slope of 0. When x equals 2, there's like a slope of 1/2 or 0.5. When x equals 3, slightly negative, so maybe negative, geez Louise, we're splitting hairs, a third. And when x equals 4, looks like maybe, I don't know, -1 we'll say. So, and then once you kind of gather all those individual points, we could start to plot them here and say, all right, we got -5 comma 2, 1.5, then we got 1, and -2 or 0, -1-ish, -1-ish, then there were 0 again, we're slightly positive, slightly negative, and a little more negative there. And you start to get a feel for what the first derivative's graph might have looked like. And so when we meet a complicated function, we're always going to fall back on this technique here, where we just estimate the individual slope at each point. Now we do have a few questions to go along with this graph. Let's see here. Question 1 here. What do you notice about the y values of the graph of the derivative when the function reaches its relative max? Well, right here is where f reached its relative max, and the y values of the derivative were 0. So I'm just going to say y values were equal to 0. Number 2 here, what do you notice about the y values of the graph when the derivative of the function reached its relative min? So it looks like right here was the relative min for f, and again the y values of the derivative were 0. So we do have that common theme going. What do you notice about the y values of the derivative when the function's increasing? Well, anytime the f was increasing, like in here, all the y values were positive. And I bet you know where the next question's going. What do you notice about all the y values of the derivative when the function was decreasing? We're going to notice that all the y values were negative, aka the f prime was living below the x-axis. So for me, whenever they give me a picture of f, in here, this originally was a multiple choice question. I've cut off all the choices just because I don't want you to be overwhelmed or distracted by them. And I encourage you to do this on a test as well. Ignore the choices for now and just start to sketch f prime on your own. The first thing that I really want you to get in the habit of jumping on is find the horizontal tangent lines. All right, and I can't emphasize that enough. When they give you f, find your horizontal tangent lines. And so I've got one here like -2/3. I've got one here at x equals 0 and then one at positive 2/3. So how does that transfer over to f prime? Let's see, if I scaled my x-axis, there's 1 and 2, so every 3 blocks is 1 unit. What I've got here is I've got roots at negative 2/3, I've got a root at 0, and I've got a root at positive 2/3. And then from there, my function f was increasing, so I know f prime's got to be living above the x-axis. Then the function decreased, so I've got to be below. Increasing means above, and decreasing means living below. So something like that would come out to be a good picture of f prime, as long as you've got the appropriate roots, and as long as you're above the x-axis when you're supposed to, and then below the x-axis when you're supposed to be, you're going to be in great shape. Here's a not a bad one to maybe try on your own. Just hit the pause button, just sketch your f prime really quick, make sure you got this one, and then come on back and see if you agree with me. Alright, I jumped on my horizontal tangent lines. I said there's only one right here at x equals 1. Bang. So I come over here, again, if I scale by the same amount, I'm going to say this f prime's got a root right there when x equals 1. And function's decreasing, so f prime's got to be living below. And the other thing you'll notice is this is a parabola, and this won't always work, but anytime you get a parabola, that's like a second degree function. The derivative is going to be linear, right? According to the power rule. The power rule guarantees that. So I'm just picturing a function just like this. And again, as long as we're below when we're supposed to, and then as long as we're above when we're supposed to, and we have the correct x-intercept, you're going to get full credit for your graph of f prime. Oh, I love it when we get to play the matching game. So we're going to go through a series of slides where they've given us 2 or 3 graphs on the same one, and we're going to try to identify who is f of x and who is f prime of x. Who's who here, all right? So let's just pick one. Let's just go with, let's pretend maybe the blue guy is f. Well, if the blue guy was f, he's got a horizontal tangent line right here, and I would expect to see f prime crossing the x-axis right here. But that's not the case. So I've just proven that blue is not the original f function. In fact, it's the other way around, and let's go ahead and test that. So the red graph is f, and the first thing that catches my attention for this function is that he is always increasing. So therefore, if f's always increasing, therefore f prime is always positive, and that's why you see the blue graph living entirely above the x-axis. So let's go ahead and say that f was the red graph, and then the blue graph was f prime. Done deal. Alright, same idea. Who's who? Who's f and who's f prime? So I'm just going to throw this out. Let's pretend that the black graph here is f. And what I've noticed is right here's the horizontal tangent line, so I'm going to expect to see his derivative crossing the x-axis right here. However, that's not the case, so I must have guessed wrong to begin with. So let's try the opposite. If the green graph is f, we've got horizontal tangent line. Does it correspond to a root? Yes. We've got another horizontal tangent line. Does it correspond to a root? Yes. So what I'm thinking is green guy's f, and then the black graph is f prime. Again, done deal. And one of the reasons I like this matching game so much and so forth, it's not a lot of work on paper per se. There is a lot of thinking going on, there's no doubt, and sometimes I have to slow down and just talk myself through them sometimes. But there's not a lot of work on paper. It's not like we're taking 18 derivatives by hand or something. But anyway, let's go ahead and try to figure out who's who here. Again, I'm looking for horizontal tangent lines that correspond to the roots of the other function. And I think, for instance, what I noticed right here is I've got a horizontal tangent line on the blue graph, and it corresponds perfectly to the root of the red graph. And we could test that theory elsewhere. We've got a horizontal tangent line on blue, corresponds to a root for red. Horizontal tangent line corresponds to a root. Horizontal tangent line corresponds to a root. So I think we nailed this one right off the bat. I think the blue graph is going to be f, and f forces the red graph to be f prime, and we have perfect correspondence. Alright, I tried to up the ante a little bit here. I've thrown 3 graphs on here, so we're going to try to pick out who's f of x. Oops, I'll grab my pen here. Who's f prime, and of course who's f double prime. And so we'll try to match these up the best we can. Again, I'm looking for horizontal tangent lines that correspond to roots, and so and this is a case where good to use a pencil because we may have to change our mind at times. I'm thinking, let's see, this blue graph has a horizontal tangent line when x equals 0, and that corresponds to the red graph's root, which is really nice. Okay, so I'm thinking red is the derivative of blue. And let's see, trace that red graph. Do you see how the red graph's got a horizontal tangent line right here? And that corresponds to the root of this greenish, yellowish graph right there. So I'm going to make the proposal that the blue graph is f, the first derivative is red, and then the green graph, or yellow graph, whatever you want to call the mustard graph here, is f double prime. And it's all about getting horizontal tangent lines, again, to correspond to the roots of the derivative graph. And hopefully I sound like a broken record, and that's the one theme that I want you to walk away from this section with. Alright, here's one I want you to try on your own. I want you to hit the pause button here. Really work diligently on this, trying to pick out who's f prime, and who's f double prime, and then come on back, hit play, and see if we agree. Okay, what I ended up with here, let's see. I said the red graph was f myself, and this function was always increasing. Therefore, his derivative lives entirely above the x-axis, which I felt was the blue graph. So there was f prime. And then the blue graph had horizontal tangents, right about here, which corresponded to the root of the green graph. So that fit perfectly. Green ended up being the second derivative. And you could also pick other points on blue. Looks like we got a slight horizontal tangent there, which corresponds to a root again, just proving our theory further. All right, we're going to switch gears a little bit. Instead of staring at the graph of f and trying to come up with f prime, we're going to do the opposite. I'm going to give you pictures of f prime, and I'm going to ask you to describe f the best you can and then come up with this graph. But before we go any further, I just wanted to take these definitions that we have in our book and just really get them crystal clear. We want to say if f prime's positive for all x within the open interval a to b, okay, I'll just make a note right there, that's open interval, then that guarantees that f is increasing on the closed interval from a to b. Okay, and then again, if f prime's negative, then f's decreasing. If f prime's equal to 0, then f is what we call a constant. And there exists the potential for a maximum or a relative minimum there at those points. Alright, I'd like to make sign charts when I see the graph of f prime. And so the first thing I'm going to do is by using the graph, I'm going to ask myself, when is f prime of x equal to 0? In other words, what I'm doing is I'm trying to find his critical points. Now, by definition, critical points happen in one of two cases, either when f prime is equal to 0 or when f prime fails to exist. Now, in this particular case, f primes always exist, so it's just a matter of figuring out when it's equal to 0. And so I said this sign chart is going to have, let's see, we've got 0 at -4, we've got a 0 at 0, and then we've got another 0 at +4. So we're going to try to describe f prime. Now all of these y values in this region are positive, so f prime's positive, which tells me that f's increasing. And then we've got a bunch of negative y values, tells me f itself is decreasing. And then we're above the x-axis, so f prime's positive and f's increasing. And then we finish with f prime below the x-axis, therefore f's decreasing. So now from this sign chart, you can tell me a million things about f. You can tell me that there's relative maxes at -4 and +4. You can tell me f's got relative mins at 0. You can tell me the intervals on which f's increasing and decreasing and so forth. Now, there are a variety of ways that you could sketch f. We could all come up with slightly differing pictures, but they should have certain common characteristics in common. There are certain absolutes that we must share. And so, if I know there's a relative max at -4, I could put the height here or up here. I could even put the max down here. I'm going to go ahead and I'm going to put my relative max right there. I'm going to put my relative min here. I'm going to put my next relative max up here. And of course the heights of those varying points could vary, but our graph should all have, similar characteristics. And so there's my sketch of f. Again, I think it's extremely beneficial to go ahead and make your sign chart. Mentally we're setting f prime equal to 0. And we're going to grab critical points at -3, -2, and +1. +1. I want you to take pride in having, the cleanest, nicest, sharpest looking sign charts imaginable. I'm going to say f prime's negative, then positive, then we're a bunch of negatives, and then we finish with some strong positives up there. So we know that f's decreasing, increasing, decreasing for a while, and then increasing. Remember, the area of this region right here tells me the amount that f decreased. For instance, we know that f increased in here, but not very much. So putting it all together, again, the heights might vary. I know I've got a relative min at -3, so maybe I'll put my relative min right here. And so the function, whoops, and I'm going to get my relative max at -2, and I've got a big min at +1. So we did some decreasing, a little bit of increasing, and then a whole lot of decreasing, and we finished with some strong increasing at the end. Again, the one thing I want to really emphasize is that this point right here, the height that I chose for that point, there's no wrong answer. I could have put it up here. I could have put it down here. As long as you don't put it higher than your max, you're in good shape. So I'm going to buzz through a lot of these next few slides, and if I go too fast, make sure we replay it and go back. I truly believe that 30 extra seconds that you put into your video and note-taking saves you approximately 10 to 15 minutes, later in the week on quiz and test correction. So put the time in now, and it'll pay great dividends later on. So we're working backwards here. F prime is always positive, and so I'm going to draw a line that's always increasing with a constant slope of 2. All right. So just make sure you draw a linear function that's got a slope of 2. You could have drawn this. You could have drawn this. The one thing all of our answers will have in common is that they'll be parallel. For this next one here, I said it looks like I've got a relative min right at 0. And so I drew some kind of parabola that had a min at 0. We've got f prime's negative, so my function was decreasing, and then f prime was positive, which meant my function was increasing. So I'm doing this without making the sign chart, but certainly I'd encourage you to do so if you feel like those sign charts help you create the graph of f. So we get a slightly more challenging here. Now again, this picture is always below the x-axis, and so if f prime is always negative, I know that f itself is always decreasing, with one slight exception. It looks like there is a moment when f prime is equal to 0, and therefore f is going to have a horizontal tangent line. So I'm going to draw a picture that's decreasing, maybe flattens out for a split second right there, and then continues to decrease. So that's the graph I'm going for. And the next one, I've got, this one's going to be very similar. We're going to draw a function that's decreasing, 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 has a horizontal tangent line, and then decreases, decreases, decreases some more. It's going to be extremely similar to the last one. It's just going to be the only thing that really differs is the rate at which the function decreases. This one's a more steady decrease in compared to the red one, but virtually the f's turn out to be about the same. Okay, I challenge you here on these two with some slightly more complicated ones. On this first graph, I've got a relative min, relative max, and then we're going to finish with a relative min. So, and again, the height, as long as we got a min at -4, a max at -1, and a min at +4, I really, the heights of those points don't bother me so much. So this graph's f prime's negative, so f's decreasing, and then increasing, and then decreasing, and then we finish with some increasing behavior. We've got that one nailed. Here we've got a relative min. Here we've got a horizontal tangent line, but the curve's going to then continue to increase. So I've got a relative min at -4. I've got a horizontal tangent line at +1. And so what we've got is f prime's negative, my function's decreasing, and then increasing. Horizontal tangent line continues to increase. So be really careful. I probably would have looked nicer if I would have dropped this point down a little bit lower, and we could have done some decreasing, some increasing, and then horizontal, and so forth. Would have looked a little easier to read. Alright, rather than giving you a picture of f prime, now I've decided to just kind of describe it using some notational purposes here. So f prime's positive, that means f's increasing. And then we said f double prime's positive, so f's concave up always for all real numbers. And then they also gave me a specific point to plot, so at x equals 1, we're at -2. And I just need to draw a function that's always increasing and always concave up. And the first thing that came to mind is some kind of exponential function. Maybe there's an asymptote, horizontal asymptote at -4 maybe, and there's a curve that's always increasing and always concave up. On this next picture, it looks like f prime's positive for all x is greater than 1, and then f prime's negative for all x is less than 1. So, if you're visualizing a sign chart, let's see, f prime's negative here and then positive here. So it looks like we've got a relative min at 1. And again, this verifies that there's a horizontal tangent line there, which we expected. We know that the curve's concave up, and we know we got a point at 1, negative 1. So right here at 1, negative 1, we know there's a relative min, and we've got to be concave up, so that's a classic parabola. Alright, we're going to finish with one really quick picture of f double prime, and I'm not going to hit you with too many of these. I think one example, and then you'll be able to run with it tomorrow. But again, when all else fails, fall back on your sign chart. What are f double prime's critical points? Alright, well, as far as my critical points go, it looks like I got critical points at A, B, and C. So we've got our A, we've got our B, we've got our C. We're going to label our sign chart here, boom and boom. And it looks like because this graph's above the x-axis, those values are positive. And then f prime, or I should say f double prime's below. And so we've got negatives, and then from B to C, f double prime stayed negative, and then from C onward, f double prime was positive. So we've got f being concave up, concave down, and concave up, and you could really run with it. The other thing that they might throw at you is they might ask you to describe f prime based off of f double prime's graph. If they wanted to do that, you'd basically have the same sign chart. In fact, let me go up here and we'll just cross that out and we'll describe f. So we know f prime's increasing, decreasing, still decreasing, and then increasing. So the graph of f prime would have a relative max at A, a relative min at C, and just a nice horizontal tangent line at B, but it wouldn't be a relative max or min. So we threw a lot at you tonight. I hope you hung in there, and we're certainly going to see a lot of graphs tomorrow in class. So good luck. We'll see you then.